welcome everybody to the workshop. But we can just launch right in, and if Simon has other things that he wanted to say right before, we can go ahead with that. With those, so yeah, go ahead.
Okay, thank you, folks. My name is Partha Ranganathan. I am from Google, and if Simon had been here, he would have given a fantastic introduction, but that's all you get about me right now. But welcome to the Data Center Energy Workshop. And this is obviously a topic very close to my heart, and it's great to see all of you here so early in the morning. So my talk is titled "A Six-Word Story on the Future of Data Center Energy," and so in case you are wondering about the title, Ernest Hemingway was apparently asked to write the shortest story possible, and he came up with this six-word story: "For sale, baby shoes, never used," which I thought was pretty cool. There's since then it's kind of a meme. Lots of people write six-word stories, six-word memoirs, and you can Google it. And so I thought, if we were to think about this particular topic in terms of a six-word story, what would it look like? And so that's kind of the theme behind the talk. I'm going to data center computing, data center energy cannot be discussed without really thinking about trends in data centers. So the first part is a six-word story on the future of data center computing, and the six words really are AI-driven, software-defined, uncomfortably exciting. I know one of the words is hyphenated, but it's my six-word story. So if you have problems with hyphenation, you can write your own six-word story, I guess. And as I go through that, I will talk about where energy comes in. And then the second part, I will kind of focus on a few examples and give some vignettes in terms of challenges for energy for this workshop to be looking at. Okay, so so the first part, I'm going to talk about the three things I said. I'm going to talk about AI-driven. I'll talk about how there is a incredible supply-demand gap. I'll talk about software-defined and how there's some opportunities in that is driving the current era of data center computing. And I'll talk about cloud as leading to some really nice opportunities there. So I think people sometimes don't realize when they are in the middle of a black swan event, but it is fairly clear to me that we are in the middle of a fundamental inflection point, a fundamental pivot in computing. And if you think about data centers, I think we are all used to this notion of Google warehouse scale computing, planet scale computing, where we are servicing billions of users. Google, for example, has I think 15 products, each serving like hundreds of millions, billions of users. And so we always been thinking about how do I deliver performance, efficiency, reliability, all at scale. And for the past 25 years, we've been doing that. But more recently, while we've always had AI in all of these products, I think we are all kind of supercharging these with generative AI. And I'm not going to belabor this. Everybody kind of knows why AI is important, whether it's consumer applications like the use of AI in email, which I seem to be using quite a bit these days, or more clearly in enterprises, where we are using generative AI, particularly to start making complex data more intuitively accessible, start having more conversational online interactions, start focusing on the generativeness of the generating content at the click of a button. There's some really nice ideas. And also AI is fundamentally transforming science. Every field, whether it's human health, software engineering, productivity, creativity, entertainment. And it comes with it some pretty new challenges in terms of how do we do this responsibly, looking at security, privacy, safety, and so on. And so as we think about all of these things, a lot of this is underpinned with larger and larger models. So we went from the very first model with like hundreds of millions of parameters to the latest Palm and Gemini models with literally trillions of parameters. And it's worth noting that as the models get bigger and bigger, with great models comes great compute. And so the compute needs have also been growing pretty exponentially. And the picture on the right shows exactly how exponential this is. And so AI is not just a fundamental.
Sorry, Partha, can I interrupt for just a second? Are you actually advancing your slides? Or?
I am. So you folks can't see things?
We're not seeing you advance. So, okay, we now just saw you advance.
Okay, can you see the slides again?
Yeah, we can see the slides again.
So this is what you missed, all the pretty pictures, supercharged AI. I flashed a slide on enterprises, flashed a slide on science. I had a really cool animation on how the models were evolving all the way from the transformer paper to Gemini. And I showed this picture, which I think is important, which shows an exponential growth and increase in computing. Okay, so you're all caught up now.
Yeah.
Okay, thank you for doing that. So all of this is really nice. So we have a new killer app in the market, and it's super exciting. But it's worth noting that we are also at a time of great challenges. And in particular, Moore's law, which we have all been very used to for the past 5 decades or so, is by any definition slowed down or possibly even dead. And this shows up in terms of technology plateaus in every aspect of technology. CPU performance is stagnating, power efficiency is stagnating, the dollar per byte on memory is stagnating, disk dollar per byte is stagnating. And this slowing supply at the time when demand is exploding is a pretty fundamental problem. And when on top of that, if you add the fact that we have some pretty fundamental security issues, reliability issues, security side channel attacks, for example, the fixes to these side channel attacks have often involved regressions in performance. Similarly, we are facing some really insidious problems around silent data corruption as you go to more and more advanced process technologies. And once again, the fix to many of these involves regression and performance. And so the combination, on one hand, Moore's law is slowing down. On the other hand, you almost have a negative Moore's law with all these additional regressions in performance. And on the other hand, you have exploding demand in computation cycles. Means we really have to think about computing, data center computing at a fundamentally different level. So that's kind of the first part in terms of the AI-driven part of the 6-word story. Now, what does that mean? What it means is we are in a new Moore's law era, and there are really 2 fundamental ways the community has been addressing this. One is how do we efficiently design hardware, and the second is how do we efficiently use the hardware. And both of this, I will submit, has a software-defined software-hardware co-design aspect to it, which is the next 2 words here. And so if you think about accelerators, fundamentally, it is about tailoring the architecture to the application, where we get, because we are so focused, we get better performance per dollar, better performance per watt, better performance efficiency. And we have TPUs, which I'm sure many of you have even used, tensor processing units to accelerate machine learning, but we have also have video coding units, VCUs, and a virtual event like this sometimes, and if you're watching this on YouTube later, there is a VCU that is transcoding all of that and accelerating that, and there is smart NICs and so on. But I think if you think about it from an energy perspective, accelerators are probably the most fundamental way to get the next wave of energy efficiency that you can look at. Across Google, when we think about the fraction of cycles, fraction of computing that we have on machine learning versus non-machine learning, we have machine learning cycles dominating the non-machine learning cycles. But from a percentage of power, the power associated for machine learning workloads is a much smaller fraction compared to general purpose computing, and it's because of accelerators. And we have had 6 generations of TPUs. But it's also worth noting, and the picture on the right shows this, we tend to kind of focus on these big accelerators like TPUs or VCUs. But if you look at Google as a workload, 1 out of 3 cycles at Google is spent on these 5 relatively small functions. And these are functions that we call data center tasks. And it has to do with fundamentally big data and distributed systems. So it's like memcopy, memory allocation, and memory movement, RPCs, protocol buffers, compression, allocations, and so on. And so there are some really interesting opportunities for energy efficiency when you think about how do you accelerate these tinier workloads? And these are fine-grained, closely coupled with the main computing. And so there's some really interesting challenges there. The second aspect is when we think about hardware accelerators, it's easy to, again, overfixate on the hardware. But as the picture on the left shows, the hardware is just a tiny sliver at the bottom. And we really need to be thinking about the entire software ecosystem. Think in terms of how do we do code design across big code bases? How do we think about the supporting ecosystem around management, compilers, tools? I often joke, if an accelerator lands in the fleet and nobody uses it, did it really land? kind of a riff on if a tree falls in the forest and nobody hears it, did it really fall, right? And it's also not just about chips. It's about thinking about systems, about clusters, issues around scaling, virtualization, quality of service, compute, storage, networking. And so this notion of co-design and having the software-defined hardware front and center is a super critical thing. Another aspect of software-defined infrastructure is how do we kind of think about designing systems so that we can efficiently get the maximum mileage out of that? And one of my favorite ideas, something that I've been talking about for more than a decade and a half now, is disaggregation. And so if you think of a system and you disaggregate it, namely you break it apart, and you think about all the compute in one pool and memory in one pool and storage in one pool, and then you wrap it up with a layer of software that then partitions this compute and decides what to do with that, that is really the essence of software-defined hardware infrastructure. And the nice aspects of this is that you get efficiency by simplicity because you're building this extremely nice, simple building blocks, and you get capability from composability because you're then combining them and doing some really nice, interesting stuff. And so again, there's some really interesting challenges in terms of how we can implement it, but tremendous opportunities as well. And at Google in particular, we've had tremendous success. We've literally had multiple Moore's Law generations of improvements by looking at software-defined infrastructure. We have several papers. We have talked about software-defined memory. We have talked about software-defined servers, autonomous servers. We've talked about this concept applied at the node level, the platform level, the cluster level, the data center level. And so, but there's some really interesting implications in terms of thinking about software-defined power management as well. And applies both to average power, but also applies to peak power. And I think there's some really nice options here. But the high order bit in terms of a broad trend for data centers is that we are in an era of software defined. It is co-designed with software, it is managed by software, it is driven by software. And so rewriting the rules of the next generation data center energy really requires us to acknowledge this new world that we are at. And then the third set of words in my 6-word story was uncomfortably exciting. And I wanted to focus on the cloud as kind of this new change agent. And the cloud really gives you a seat on what is this new roller coaster with the end of Moore's Law, but kind of democratizes access to everything, right? And so you have on one hand, you have big data, you have big scale, you have open ecosystems, and it kind of creates a bunch of really nice opportunities at the data center level. And in particular, I wanted to call out 3 things. One is this notion that it's about digital transformation. So basically, people, we kind of have multiple epochs of cloud. And initially, it was all about just kind of getting machines moved to the cloud and so on. But now it is no longer just a hardware story. It is about fundamentally transforming an organization's business by digitization, using AI, using kind of all the data there, using app modernization and so on. So there's some really exciting opportunities that come when you think of cloud, not just as a hardware replacement, but as a transformation story. And correspondingly, some really nice opportunities for the research community as well. And then the second one is this notion of what do we think about the data cloud? And we have traditionally focused a lot on computing, but thinking about data-centric data centers, understanding how we use data. Most enterprises get a fraction of the insights possible from the data that we have, and thinking about the data lifecycle all the way from warehouses, data lakes, lakehouses, streaming data, AI, ML, some really nice opportunities there. And then finally, trust and security and reliability. And I always remember my colleague who runs the security group. This person pointed out that the hackers have bosses as well. And it was kind of a really wake-up moment for me because security is a moving target. And I think there's a lot of opportunities here as well. So that is the very quick overview of where the data center space is going. And the 6-word story really is AI driven. So we are in a world of fundamental change with AI changing the assumptions and changing the assumptions when at a moment when technology is slowing down. So there's some really big change associated there. Software-defined hardware, both in the context of thinking about co-design for custom silicon and accelerators and vertical integration, but also in terms of software-defined hardware for disaggregated systems. And uncomfortably exciting, cloud and the fundamental changes it brings in terms of thinking about digital transformation, data transformation, and new security and trust challenges. And throughout all of these things, power and energy are oftentimes the gating function there, or oftentimes there's tremendous opportunities to be able to do much more efficient stuff as well. So with that as a context, so now I wanted to focus on data center energy, and I thought I would kind of again use the same 6-word story, and I'm going to use the same 6 words, and I'm going to use those words to give you 3 vignettes. And I'm going to again use uncomfortably exciting, software-defined, AI-driven future. And I'm going to reverse the order a little bit here. So uncomfortably exciting, the vignette I wanted to talk about is this notion of sustainability. And I see some people here in the room who work a lot on sustainability. So hopefully they're happy that I'm flagging this a little bit. So we as a community have spent a lot of time thinking about energy efficiency. But when you think about what happens with the energy, and we think about some of the most important challenges facing the world around climate change and sustainability, and when you think about every major data center provider, whether it's Google or Amazon or Microsoft, all of us have pledges around carbon. And Google in particular, we were the first to have a very audacious goal of 24/7 carbon-free, 24/7 net zero carbon by 2030. And these are pretty ambitious goals. And so typically when you think about sustainability, you think about this notion of scope 1, scope 2, and scope 3. Scope 2 is basically the electricity consumed and the carbon impact, which is something we all spend time on. But scope 1 is basically the emissions from the data center itself, like the diesel and so on. And scope 3 is the embodied energy, the embodied carbon. And that is something pretty insidious and very challenging. And so we have some pretty significant challenges to up-level our conversation on energy to starting to think about the implications on sustainability as well. And so I think that is vignette 1. Vignette 2, picking software defined as the 2 keywords. One of the big techniques in recent years on the data center space that has been super effective has been around oversubscription. And I have pointers to a couple of papers at ASPLOS and OSDI where we went into detail on some of the challenges there. But really thinking about an oversubscription, as a quick background, what we try to do is what the airline industry used to do. You sell more tickets than you have capacity for, and you leverage the fact that statistically, not all the capacity is used, and so you can actually get more out of less. And so in the rare case when you end up selling more and actually needing the demand, then you start shedding load in some form, right? And so there's some really interesting challenges around power over subscription in terms of looking at the continuum of knobs and actuators to manage power, whether it is power capping and load shaping at the real time, all the way to task migration at the next level of stuff, to even possibly rack migration and physical infrastructure migration. So there's some really nice opportunities there. And how do we do that with resiliency and appropriate SLOs? I think there's some very nice opportunities there. And then the second software-defined opportunity for power, and I picked an example of something that we call platforms-aware AutoML, and this was a paper at ASPLOS a couple of years back. And the idea really is, we all know what AutoML is, which is basically trying to kind of using ML to determine the model that we want to use. And being able to have an awareness of the hardware platform, when you kind of go through the design space exploration, turns out to be incredibly more efficient. And we have shown double-digit significant energy efficiency improvements by thinking about co-design and software-defined hardware in the context of platforms-aware AutoML as well. And then the last part is AI-driven. And while we spend a lot of time thinking about infrastructure for AI, it turns out that using AI to improve infrastructure is equally effective. And this picture shows an example of how we used reinforcement learning and machine learning to optimize data center cooling. And for those of you who follow data center cooling, we have this metric called PUE, the power usage effectiveness, and it's an incredibly optimized metric. And the fact that we were able to get like a 15 to 30% improvement on top of what is a mature field, bodes really well. And so we've been seeing the application of machine learning for task scheduling, the application of machine learning for hardware design, the application of machine learning for anomaly detection. I often joke, everything tastes better with a sprinkle of ML on top. And so I think there's a lot of really cool stuff that we can do there. But it also comes with some really interesting opportunities and challenges. Because ML is not a panacea, and you have to use it very cautiously. And in particular, on the schooling case, I always point out an example where in the middle of winter, the ML was operating the chiller at higher and higher speeds. And when we looked at what was going on, we realized that there was a de-icing algorithm that was running. And the de-icing algorithm was basically changing some local sensors in a way that the machine learning algorithm thought like, hey, things are getting warmer, so I need to kind of ramp up the cooling. And so the chiller was operating even faster. And the de-icing algorithm was like, well, I need to do more de-icing. And so there was a vicious cycle of stuff here. And so sometimes you have to be careful about how you do that. And again, at Google, we have spent a lot of time thinking about it. And in this particular case, we ended up actually increasing the hyperparameters and doing stuff. But it's also important to think about how can you do better than control theory when data is driven by control theory. And there are some really nice techniques we use there. And also, how can you have multiple tiers of checks and balances for safeness, fairness, usability, bias, and so on. So again, lots of opportunities for us as a community to be spending more time thinking about it. So again, I picked 3 vignettes because Simon and Thomas gave me only 20 minutes, and I wanted to kind of set the stage for the rest of the discussions. But as I said, this is an area I've been working on, and this is just the papers I have written in the last 10 years. And so you can see there's tons and tons of conversations we can have here, and hopefully in the rest of the bookshop, we will have those conversations. But I wanted to pick one of my favorite papers in this space, and this is actually a paper from more than a decade back. And it was called The Recipe for Efficiency. And I used to be young at that time, and I was very optimistic. And I said, hey, look, I can write the definitive paper on how to do energy management. And it's an interesting paper because it basically says all of power management and energy efficiency research can be summarized into 4 big problems we are solving. And all of energy efficiency optimizations can fall into one of 10 different approaches that we end up taking. And I found that it has stood the test of time for the past 10 years. Every paper that I write, every new paper I write, I go back and I find that it uses one of these techniques. And I'll encourage you to read the paper. But in particular, I feel that techniques 6 to 10 in this list have been underutilized in the data center space. And I think there's lots of really nice opportunities to go beyond traditional energy management to starting to look at more alternative energy management techniques as well. So with that, thank you again for the time. The key takeaway really is we are a pivotal moment in the era of data centers, and correspondingly pivotal moment in data center energy management. The really 6 words you need to remember from the talk is AI-driven, software-defined, uncomfortably exciting, and that is that 6-word story. So hopefully, let's write the story together.
Thanks very much. I think if there's a time for questions. I don't know, Simon, if you wanted to take over, but
let me see if I'm. Am I back?
Yes, you're back. Okay, actually, I was gonna do the introduction to Partha that I forgot to do right at the beginning, and my apologies for that. So Partha's written the book on data centers, and we actually use it in our classes here. So we really thank you very much for putting that together. So great talk. Anyway, so I thought we'd if we have time, we could open up for a question or two.
Yeah, let's leave a few minutes for questions.
Okay, and people can either put it in the meeting chat, or it's a small enough group that if you just raise your hand, I can call on you and you can talk in the thing as well.
I think I had one question sort of motivated by something that you had said about using AI towards improving energy. It's like one aspect of this is to be able to, if we're going to control energy, like sometimes it's really very difficult to tell what's going to happen if you make some change. Oh, you move an application from one place to another, or so forth. I don't know if you've had success in being able to take our existing systems and use AI to be able to predict outcomes of control changes on energy. So
yeah, no, I think it's a really good question, and this is what I meant by when I said, how do we use control theory to determine the limits of control theory? Because the data that we have is all, by definition, data where things are working. And so we don't know the place when something will explode because we have run the temperature too high and so on, because we don't have that data point. And we don't want to figure that out by using machine learning in the wrong ways. And so one of the ways we have tried to work around that is this approach of incremental perturbation, where we kind of try to look at the boundaries and then we perturb things where we can kind of start seeing some of that, and that has been very effective. But again, ultimately, we need to have multiple levels of checks and balances. And in the data center space, we actually have like human intervention so that we can control some of these things. But we also have more recently multiple levels of MLs, checking MLs, and so on. So I honestly think it's an open area of research where we could be doing a lot more, but there are some beginning principles that are starting to emerge that can be a foundation there.
Cool. Carol Jane, if you wanted to ask a question, go ahead.
Yep. Thanks so much for organizing this workshop to start with, and a very inspiring talk, Partha. I was really excited to hear about power, energy efficiency, and all of that. I guess, and you mentioned sustainability. I was very curious about what's your view on how sustainability could play a role in that 10 guiding principles for optimizing for, I think, operational efficiency for data centers, and how would sustainability, manufacturing, embodied carbon change the equation?
Yeah, that's a good question. So I think what I'm hearing you say is you're asking me to write a new paper on the 10 principles for sustainability. So challenge accepted there. But I think, Carol, so if you read that paper, fundamentally, when you're thinking about energy efficiency and power efficiency, the principle, I can summarize it in 2 words: avoid waste. Because if you figure out where you're wasting things, that is where you get most of the benefits. And from a sustainability point of view, if you up-level it to kind of thinking about avoiding waste in resources, you end up getting the same thing. But where I think we need to revisit the principles is the supply, like for example, transportation, the definition of where waste happens, or when you look at some of the materials trade-offs in carbon or toxicology and so on. So sustainability is a much broader space. So I do feel that the fundamental principle of thinking about where waste happens, the why of waste happens, and the techniques to reduce waste apply. So those 10 principles I think will apply. But I think sustainability will probably be a superset, and I suspect there are going to be 5 other principles which acknowledge the fact that sustainability is a broader problem statement and includes things that we normally don't associate when we think about resources.
Cool. Thanks.
Thanks. So Simon, I know we are over. Do you want one more question or move on?
I think we should probably move on. Thank you so much, Partha. Partha is going to hang around for a couple of hours, so I think if people have more questions, feel free to put them in the chat, and Partha can answer them there. We also have a Slack channel. I was going to mention that in my intro, that people can also ask questions, and we can use that even post-workshop time to discuss things. So thanks again, Partha.